Okay, now that we've done Vesper theory, we're going to get into some more complicated theories that explain some things that Vesper theory can't. So there are multiple bonding theories. And remember, the word theory doesn't mean, oh, this is the theory, this I think explains this. It's actually backed by a lot of evidence to explain what we see and why we see it. So we already talked about Vesper theory. Now this is a valence bond theory. It's a little bit different, but it kind of fills in some gaps that Vesper theory leaves. So Lewis dot structures, Lewis theory, we'll call that, is a simple way to visualize arrangement of electrons in a molecule. It's like 2D, right? That, of course, had some shortcomings because it doesn't actually show or explain the differences in covalent bonds. These all look the same. The bond that you draw between HH, HCl, and ClCl are all the same. You just draw a line, it's sharing of 2 electrons. And that's not actually the case. Valence bond theory shows that when atoms share electrons, when their atomic orbitals overlap. So it's not just that they're sharing electrons, it's that their orbitals overlap, and that's where the sharing electrons happen. So this is just going a little bit deeper. Okay, so in valence bond theory, a bond forms when single occupied atomic orbitals on 2 atoms overlap, meaning you have one over here with 1 electron, one over here with another electron. They overlap to share, so they both now have 2 electrons. Okay, they just overlap. The 2 electrons share in the region of orbital overlap must be opposite spin, so one's up, one's down, just like all of our other electron configurations. The formation of a bond results in a lower potential energy for the system. That just means that it's more stable when this happens. And we know that orbitals that have 2 electrons in them, one up, one down, are going to be more stable than ones that only have 1 electron in them. So what this is really showing is, so for an HH bond, for example, which is what this picture is showing, hydrogen has a 1s1 and the other hydrogen has a 1s1. So what happens is when they get close enough, those hydrogen 1s's will overlap. And now they're sharing, one switches spin, so that they're opposite spins, and now they are both very stable. This gets much more low energy. So a hydrogen-hydrogen bond is a 1s and another 1s overlapping to make 1s2. Fluorine-fluorine bond would be very similar. It has a 2p5 and a 2p5, and then one of those p orbitals in each will overlap so that they have 2p6. Same thing with HF, only they're different orbitals, a 1s1 and the 2p5. One of the p orbitals will overlap with the s orbital. Everybody's happy, everybody has full orbital. So that's kind of what valence bond theory is getting at. Okay, so it kind of explains some of what we see as well. So hydrogen selenide, for example, this is like, it's got a similar structure to water, but H2SE is a foul-smelling gas that can cause eye and respiratory tract inflammation. The HSEH bond in H2SE is approximately 92 degrees. Okay, that's about 90 degrees. If I'm looking at this molecule, why would it be 90 degrees? Okay, that would be like square planar angles, right? So use valence bond theory to describe the bonding of this molecule. Why would it potentially be 92 degrees instead of, let's see, this looks like water. It should be like 109.5 or 104.5 maybe, but 92, that's pretty small. So we're gonna look at, it says use valence bond theory, which is the theory of them overlapping, to describe the bonding. Well, hydrogen has a 1s1, so we have 2 hydrogens that have a 1s1. Oh, I drew it down here. There we go. And selenium looks like this. So its 4p orbital is the one that is missing electrons. So it actually needs 2. So one of the hydrogen 1s's will overlap with this p orbital so that they're both full. And the other hydrogen 1s will overlap with this p orbital so that those are full. Now everybody's full, everybody's happy. Now, why does that explain the 92-degree angle? Well, p orbitals, the 3 p orbitals look like this. One goes up and down. Remember, they look like dumbbells. One goes side to side and one goes front to back. That's the X and the Y and the Z axis, okay? They are all at 90 degrees from each other. So if one of these orbitals, say the up and down one, and the other one, the left to right one, are the ones sharing, then you're gonna get about a 90-degree angle. So this valence bond theory actually explains some molecules, like this molecule, having different angles than what Vesper theory expects. So this is kind of a little bit more in depth and explains some of the other anomalies we see that don't fall under the Vesper theory. Okay, now there are some shortcomings to this valence bond theory as well. They only explain some covalent bonds. There's other ones that's like, well, that is not explained by the overlapping of orbitals. For example, BeCl2. So if I drew BeCl2 for Lewis dot structure, it looks like this. Be's is 1s2, 2s2. Well, those are both full. So why does it bond? Why would it bond if beryllium doesn't actually need any electrons? Okay? That's kind of one question that we could pose. Also, carbon dioxide, this is linear, right? Well, we know it's linear according to Vesper theory and observation. But if I got a 2p2 in carbon and each of the oxygens has a 2p4, we would expect different angles because of those p orbital overlaps. We would expect some 90-degree angles, right? And that's not what actually happens. We see a 180-degree angle. So we need different theories to kind of explain different things that we see. So when I have you explain something in a question, I might be like, use Vesper theory or use valence bond theory. So you do have to know the different theories.